I think storage is the soul of the server. And that sounds super fluffy. But if your data is gone, it's gone.
I was a Perl guy before Python.
Yeah, me as well. It was better than shell script. There was a lot of work for the developers following that.
Now we're giving a lot of ideas to hackers or wannabe hackers. Like, hey, how about we test?
Welcome to Cisco Tech Stories, a podcast with real-life stories from real-life engineers. Your hosts are Nicholas and Tristan. In today's episode, how a monitoring script can take out an entire data center.
Hello and welcome to the Cisco Tech Stories podcast, where we interview Cisco CX engineer about the crazy troubleshooting stories. My name is Tristan. I'm a Cisco technical leader in the service provider team in EMEA TAC. And I'm joined today with Nico. Hello, Nico.
Hello, I'm Nicholas, a wireless technical leader in TAC as well. And today we continue our data center rampage by welcoming Kris Vandecruys. Welcome, Kris.
Hello.
Can you please tell us a little bit?
Thank you for having me, guys.
Can you please tell us a little bit about yourself?
So if the voice sounds familiar, I'm the guy that does the voiceover for this podcast, but I'm also a Cisco engineer. I was with Cisco since 2010. I joined as a TAC engineer in the then storage team, the storage area networking, actually. I did that for about 6 years. I became a technical leader for the data center space, did a bunch of odd projects for Cisco, all over the place. Officially, I'm not an engineer anymore. My title is business architect, but I'm still an engineer at my core, in my heart. And I wanted to share this story as well because I think it's an interesting one, and I hope you guys think it's the same.
Tell us a little bit more about the storage. What storage exactly?
So storage is actually a sort of a really big domain, and it's niche. Not a lot of people will have heard of it, unless you're like within. I have a background in financial institutions, and there it's super common. The general idea is that somewhere in the 80s, 90s, we started having servers, Windows, Linux, Unix, stuff like that, and they had internal hard drives. Now that's great because it's all directly connected, low latency. You have easy management, but the problem was that you had a full stack in each box that needed to be managed for regardless which application. So say you have a file server, one thing that needs a lot of storage, but you also needed a CPU in there, you needed memory, you needed extra resources to make the thing do what it needs to do. On the other hand, you might have something like a proxy server, something that just needs a little bit of storage, pretty fast storage, but does a lot of processing because it needs to apply rules to that. So you could never build a one-size-fits-all server. And the general idea around servers was that you came into a situation where you either had over or underutilized resources on quasi every box that you had in your data center. And we moved into a system that's more decentralized. We had more powerful networks. And they said, look, it would be really nice that we put that storage in a network as well. We centralize it in a big box that can be carved up in little pieces. We call those LUNs, logical units, and we provide them through a dedicated network to the servers. Those servers had special network cards. We call them HBAs, and they had a special network over there that is FiberChannel. FiberChannel was really cool in the beginning because it was about twice or 4 times the speed that you could get over an Ethernet network. It was low latency. It was just very performant. It was all across optical fibers, hence the name FiberChannel, but you can theoretically do it across copper as well. The general idea was that with storage, you had a centralized management place for everything where your data lives. That means you could do backups centrally. You wouldn't need to go across the network to all your different servers to get the data. You could get benefits in replication, where, again, background in finance, you would have 2 sites and they would have a long distance replication. About 40 kilometers it was for the situation where I was in, and that happened synchronously. There was short delay, so you didn't have the throughput that you had. And there's a number of workarounds around that idea. But the general idea was there, you take all your storage, you put it in a big box, you put a network in between there with some logic, and then you add a management layer. So you can adjust each server's storage needs individually. That's a little bit the domain that I was an expert in. Before I joined Cisco, for me, it was mostly the boxes, managing the storage itself, less the network. Like I said, it's a niche domain, so there's not a lot of engineers, at least in Belgium, not that had that expertise. So Cisco asked whether I wanted to help them out on the storage networking, and I still learned tons there. So I felt coming in like an expert, and I very quickly got schooled by Cisco that I was not. Fortunately, they gave me the expert to again get that feeling.
And actually,
expert in the technology.
I'm impressed by all of those sub technologies in the data center space. Like my innocent and non-professional mind in data center, I was thinking that, okay, storage is just hard drives inside the server. And then I discovered that it's actually a totally separate network, FiberChannel. Does that even run on IP, or is that even something totally separate from IP networking?
It has its own protocol. You can do it on IP. So there's multiple sub-protocols in there. So you have something called iSCSI, which is literally SCSI packaged in TCP/IP. Very practical, runs basically across everything. The disadvantage there is you have a lot of overhead. Big headers. You have an IP header. You have a TCP header. You have whatever layer 2 network, Ethernet, or whatever that's in between there. FiberChannel is really slim. It's just like a layer 2 header, a block of about 2 kilobytes of data, and then something to end your frame with. So it's a switched network. It's not routed. That's sort of one of the disadvantages in there. And the funny thing is that you naively assume that the hard drives are always in the server. The last few years, we've been making a motion in the opposite direction again. So there is a technology called hyperconvergence. Nutanix is there, VMware is there, Cisco is there. We have had a product called HyperFlex that serves that market. And it's basically classical servers, but with a distributed management layer. So they have all their resources internally, but they can also share their resources through the magic of virtualization and virtual machines and containers and all that through different physical hardware. So it breaks down the boundaries of those hardware boxes by adding a management layer.
So that means that you can have the storage onto the server itself, but it doesn't necessarily mean that it will store things for its own use. It could be storage that will be used on other servers. Is that right?
Exactly. Yeah, you would say, I want an easy to manage server environment. You would buy 16 boxes or so. Each of them are equipped identically, most of the time identically. They have a lot of RAM, they have a lot of storage, they have a lot of compute. And then through virtualization and vMotion techniques and redundancy, a lot of that data that gets stored on multiple boxes in the system, is across different places, wherever it's needing to be. So if you would move workloads from one physical machine to another, or you would run your workloads concurrently on several different machines, they would access the same virtual pool of disks, even though they are on physically separate machines. Yeah, they don't necessarily own it, and you need that management software to track where everything is.
Thank you. It's excellent introduction. I learned a lot already, so I'm curious to see what story you have for us today.
Yeah, I want to talk about the only showstopper bug that I ever filed as a tech engineer. We can enter bugs in different severities, regardless what the impact is that the engineer thinks it will have on the network. I entered that particular bug as critical, which was the highest level that we have added. And then the developers add a priority to how quickly they want to fix it. And to my surprise, this got flagged as showstopper, which is their severity 0. That just tells you a little bit about how bad the situation was. But to fully understand that, what we're going to need to go through a few more topics to say is like how can a storage network, where I talked about how it's redundant. In FiberChannel, what we typically do is we do everything in double. We have an A network and a B network. We have in our devices separate redundant components. How is it possible that you would have a single bug that is so critical that you take a network that is built with robustness in mind, from its very foundation to the execution in the thing, in the data center, that you would end up with something that is very critical? And I think it's important to know that a lot of Cisco data center boxes run an operating system called NXOS. NXOS has a long history, but what it is basically is an embedded form of Linux. It boots a small Linux kernel. It has a lot of the services. You can, if you have the right tools, you can open up the hood of your Cisco device, your switch or your storage switch or your router, and then drop into a system that is basically supporting ls and cd commands, which works like a Linux system. It's stripped down.
But a small question there, because iOS XE is also Linux behind it, right? But we hide it, right? It's you're not supposed to give access to anything, etc. So what's the difference there? NXOS, is it a bit more open? Like you can install modules or whatever?
It's modular in one hand. I think a lot of it is, there's got to be different development teams behind it. But some customers really prefer the word iOS. NXOS was intended to be like the next generation, hence the NX, where they would leave behind some of the baggage that was gathered on iOS. The storage line of products, the MDS switches for Cisco, was relatively new, and they came with their own operating system called SAN OS. SAN OS was, in essence, also a Linux. So what they did is they sort of moved into a more Cisco mindset, the typical show commands that you see. NXOS was built and bred on SAN OS. And even though it's a Linux kernel in iOS and a Linux kernel in NXOS, they're developed as separate products. I think over the years, these things are growing more closer and closer together, where pure iOS, like Catalyst iOS from the 90s, was not really Linux-based. It was a homegrown operating system, where now you really have that separation layer between there's an open source foundation, there's a shell across it that looks and feels Cisco, and then on top of that there's all the functionality that you would expect. But I think we in a lot of products we do Linux. If you look at the server space, the thing that Ricardo talked about last time, the management layer there is also a Linux layer.
Everything's Linux now,
Yeah, everything's Linux. I think the second interesting thing to do, and I'm not sure if that is in the iOS space as well, but in the NXOS space, it's super common, is that we separate control plane and data plane. Meaning that the thing that the device does, switching or routing, happens on modules that do only that. But everything that goes across there, like SSH, like time synchronization, like your management software, that runs on separate modules, the control plane. So there is on one hand a redundant, two servers actually. You can think of it as really two servers that program the rest of the hardware of the switch. So that if those servers go down, for instance, a reboot or something, the rest of the module stays working. So the switch keeps on switching. It only is once you start hitting timeouts. In FiberChannel, for instance, there's a sort of a hello protocol that happens between the different devices. They form a fabric. So they know about every device in the network, but they need to make sure that they synchronize that information. There's a timeout, and you need to make sure if you do an upgrade, your control plane cannot go down for longer than the time it takes to do that upgrade in there. So you can do live upgrades, everything stays working, but the key there is that you need to respect like the underlying protocols concerns about timers and everything. And then the final thing I think is important is that a lot of these devices are still managed with SNMP. And SNMP is an old protocol. I think we can call it an old protocol. But it's functional. It's very stable. It's very mature. And in its core, it's sort of unwieldy. So it's large strings of numbers, 1.3.6.1.4.1, etc. And each of these numbers adds to a branch of information in a repository. And a lot of the things that you need to manage your switch, either read or write, you can execute by reading or pushing into that SNMP tree. You can change values in that large management tree, and that reflects something that you would do with a config command inside your management interface. I think we have sort of set the stage. We have a highly redundant network that both is executed in double. Because at one point, if something goes wrong, I think let's scroll back a little bit to storage. I think storage is the soul of the server. And that sounds super fluffy. But the point there is any other component you can replace, reboot your server, and it comes back the way it was. If you take out your storage, you lose your data. You can't just swap out a hard drive because you swap it out with a blank one. You need to make sure that the bits and the bytes that are on there remain available, that they remain in the state that they were. Otherwise, your server loses its purpose. So I think storage is an interesting domain because it's the one thing where losing a single bit of data has an actual really large input, because those bits and bytes are somebody's bank accounts or somebody's family's photos or somebody's notary documents, important real world stuff. If you lose a few frames in a network, no biggie, you send them again. If your CPU fries, okay, you replace it. Make sure that you don't walk across the carpet and everything. And then it ends. But if your data is gone, it's gone. So you need to have extra copies. You need to make sure that there's multiple paths to access it towards. You need to make sure that the management that manages all the logistics of that data is redundant. And despite all these things, it's still possible with well-tested, solid, open source, old technology that you still find things that have a big impact on that. So let's scroll back to, I think, 2014 it was. Might be 2013. At one point, I get a severity 1 case as a TAC engineer. I pick it out of the queue, and the customer says, look, your switches crash when we run our monitoring software on them. And I'm immediately like, that's not supposed to happen. So you ask the customers, like what happens? It's like, yeah, we have monitoring software. And as soon as we start a scan of the storage network, it goes out completely. And I'm like, completely? Yes. Fabric A, Fabric B, controller A, controller B, it all goes out at the same time. So we start investigating. You go onto the switch, there's a core dump there, and there's not a lot of information. You really notice is like the point where it's crashed, it didn't leave anything in the logs. There was no logging information. There was nothing that shows like any of the processes crashing. You just see supervisor one of those two control planes drops out, blinks out into existence. Few seconds later, when you expect the other one to take over, because they synchronize the data with each other so that they're always in the same state. Few seconds later, second one goes out, and it happens on both the networks at the same time. Now that both of the networks on the same time, I'll spoil that surprise already, is that was the customer's fault. They ran their monitoring software on a contiguous IP block, so 254 addresses. They started at 1 and they went up to 2054. They started at 2. They probably have a gateway or something in there as well. And what they did is they added the odd addresses on one side of the fabric and the even addresses on the other. So they did left, right, left, right, left, right. And they just pew, 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 shut out every switch in the network every time that the monitoring software starts.
So are you saying that they should have had 2 monitoring systems that were separate, each monitoring one side, or?
So the general approach that you do with redundant networks, if you have a left side and a right side or an A and a B, it says, look, you never do something on both sides at the same time. You will do all your odd addresses first, you wait 2 hours, and then you will do all your even things. Now, you generally wouldn't do that for monitoring. You would do that for configuration changes, or when you make some sort of modification to the system, you would leave ideally 24 hours between A and B side, unless it's something that really needs to be synchronized, which is very rare. You would keep a safe distance in between there. But they are like for monitoring, for doing a read operation.
That can hurt, right?
That can hurt. It's like that's impossible that could touch it. Um,
Out of experience, that's not true. That's already wrong from the get-go.
Yeah, indeed. The best cases, and I guess a lot of your guests will say that, are the ones where you go and you say, that shouldn't happen. Where you have this expectation of, this is not something that you would expect, something that you were trained or learned to do, or something that makes you scratch your head and think is like, where do I start here? So we did all the standard things. It's like we got network captures of the SNMP. We got debug images loaded on the switches and everything. That gave us better core files. So when an operating system crashes, it dumps its memory into a core file. Fortunately, we had that, and we were quickly seeing is like, look, this is because of SNMP. We had on both sides the confirmation, nothing happens. If you don't do SNMP, the moment you started questioning in SNMP, you saw a crash in the server. Now, the thing is like, what is it exactly that they were doing? And it turns out that their monitoring system wasn't really a monitoring system. It was an intrepid local system administrator that had written a Perl script. Perl is like a programming language that you can very quickly build things with. That was very common
Python.
before it all became Python.
I was a Perl guy before Python.
Yeah, me as well. It was better than shell scripting. So everyone knew Perl, even though it was like completely unreadable after a week of not looking at it. But Perl was an interpreted language, and it didn't really have types. It had the idea of an integer. It had the idea of a string. Our systems are built usually in C, and they are strongly typed. You need to make sure that exactly what is going on there. So what we noticed is this guy, when he started writing these things, he also didn't have a very good understanding of FiberChannel. Like you have in a switch network, like you have in Ethernet, they have VLANs, logical separations between your network. On FiberChannel, you have a similar concept. You have vSANs, something that Cisco invented. It's a name that some other networking computing company later stole for their storage layer, but we were the original vSAN people. And a vSAN is just like a tag, something that goes inside your network. It says, I belong to network 2, I belong to network 10. It goes up to 4096. So it fits inside a 2-byte integer. Turns out that Perl didn't really care too much about all that. And the guy says, okay, I will go, and this is an off by 1 error actually, from 0, which isn't really a vSAN, but that doesn't matter because you'll just say, okay, this node isn't found in SNMP, up to 4096, which is 1 bit longer than you would be able to fit in what we expect to get for a vSAN. So the highest number you can get is 4095. And this guy says, okay, went up to 4096. Perl didn't stop him from doing that, and asks for 1 bit larger. Now, what happens at that point is the SNMP implementation gets that value in, has a 32-bit integer for that, takes that in happily, passes that 32-bit integer into the underlying Linux operating system, where it says, look, okay, this variable that we use to store the vSAN number inside the process that controls the vSANs has a 2-byte integer space in memory reserved for it. So what happens is, because you got 1 bit over, it started reading from memory it's not supposed to, and the underlying Linux operating system says, nope, I'm not doing this. This is bad. And just crashes. That's why we have the redundant supervisor. But what happens is they synchronize with each other, and there's a queuing system. So every unhandled request goes into that queue. Queue gets synchronized to the second supervisor. They're like, okay, other guy's gone. I don't know why, but I'll just continue. What's the work? What's the first thing in the queue? Okay. Read vSAN information for 4096. Does exactly the same thing. Takes down the entire switch. That had ripple effects, because if these switches drop out consistently, when you try to start them back up, they become difficult. They're like, oh, but that guy was there and he's no longer there. And am I a different network? And I have to go back into discovery mode. And their script just kept on running in the background. So it went back down, and they had the biggest difficulty just to just stop it, clean everything out, and bring it back up, because it kept on going between crashes and recovery attempts, and everything was working against each other. I think the main lesson here is if you work with data types, make sure that you know exactly what you're doing. But that was a bug that could cause anyone with zero privileges, just the ability to be on the network and send one frame of SNMP, they could take out an entire data center. Fortunately, that bug was fixed. We had a couple of reoccurrences over the years, but that just gave an error message or the process restarted. We never had full data center outages. But for the longest time in that version, we were really scared that customers were messing around with homegrown scripts that try to be smarter than the engineers that built the product.
It kind of reminds me one of the many problems of SNMP, because we could have entire episodes about why SNMP is too old school, is sometimes you have an OID that's a specific value, but that's not just it. That's a table or whatever. And then you need to add dot a number, and that's like an IP address or a MAC address. So you cannot predict in advance how large are your tables. You cannot predict what's the maximum value, etc. It's really hard to just name an OID when the end of the OID is just a number in the table. So
you have the MIB files for that are supposed to help, and that usually makes it a little bit easier to get the right values in and out. But again, if you're young and eager and you start saying, "Oh, I'm going to write this really cool monitoring system for my boss," and happen to take I had a rough time with getting that bug approved and everything, but I don't want to think about the rough day that poor engineer had explaining to his manager. Is like, hey, remember that project that I was allowed to do? Oops, it took out our entire business for 3 days. Again, not supposed to happen, but you learn a lot from these cases.
Yeah, that talks a lot about automation as well, right? Like there was a famous social network recently that went down because of a script like that. You think you're doing a small maintenance task, but your script goes a bit off the rails and the network goes off the rails.
It's interesting, and especially because in a network that is meant to be so robust, to have such a little thing slip by the rails. The funny part about the ripple effects, I mentioned, like we saw this bug years and years after, it was not necessarily in storage. It was in other NXOS products. Because they all come from the same pedigree, suddenly you had data center switches, which had similar issues because they supported FiberChannel or FiberChannel over Ethernet at a certain point. You saw that in the server platforms because the servers have Cisco UCS servers are fully integrated. They know how to speak FiberChannel as well. They knew the concept of a vSAN, so you could access that. We saw the same thing happen in other things where it was possible to force a bad typecast in SNMP on other numerical values. So that had a big ripple effect for something that is like 1 bit off. There was a lot of work for the developers following that.
Now we're giving a lot of ideas to hackers or wannabe hackers. Like, hey, how about we test every device with every SNMP value and see what happens?
Well, the fun thing is we did that. We went through that effort back in the 2010s. And I believe that's even now part of the standard testing suite. I would need to verify that. But I know that for a really small bug, it had a lot of consequences in how we started changing those developers. Also, I'm pretty sure that most hackers will also start testing products for these things long ago. That we know that off by one errors, that messing with types between C and non-C programs is a concern. It's something that I learned in school in the 90s. Is like, make sure that you check your types always to make sure that you don't get into these situations. This was one small thing that slipped under the covers. So I'm pretty sure that, yes, probably might be products to do that. But on the other hand, we have a lot more mitigation that it doesn't take down an entire data center. It will cause an error in a log line.
No later than yesterday. It's actually funny, the story that you just tell, because no later than yesterday, I was reading an article online about software security, software vulnerability, and all that along. And one of the sentences that struck me, and that's totally true, was that assume that every input, whether it is user or machine, assume that every input is invalid, and be prepared to handle invalid values, all type of invalid values, like letters when you expect numbers, numbers bigger or lower than the limit. Check everything for all possible conditions, because if an input can be wrong, then it will be wrong. Somebody will make it wrong, whether intentionally or not. And well, like in your case, it was unintentional, sorry. But if a malicious user just wants to do, okay, let's see if I put a -1 value here, what happens? That's pretty bad. So yeah.
That was the WinNuke thing we had in the early 2000s, where if you would swap the source and the destination address in an IP packet, then you would crash a Windows server. Again, something they didn't check for, something that didn't happen, and it's a difficult mindset, I guess, to live with the idea that not every user will be malicious, but there are a lot of malicious users out there, and the ones that aren't malicious might be stupid enough to try things that you would never have considered anyone attempting.
What's also coming to my mind is beyond abusing values and so on, there's a CPU aspect to SNMP. That's what we still see a lot in the enterprise. People have several monitoring apps sometimes because one third-party monitoring app does this, another app does something else. So they have a lot of management overhead on their device. And SNMP doesn't really care about CPU utilization. It's going to poll for values. And if it polls a lot, your device is a lot busy just responding to all those queries. So it can be spammed a lot. So that's why I think the whole networking industry is moving to telemetry, where you're asking the device, you're registering, you're saying, can you please tell me this information on a regular basis? And you don't, just spam the device, which is a lot better on the CPU. And then you can also compress this data in binary and not have simple text like SNMP and so on. So at least that's what I see a lot, people causing high CPU because of over monitoring of their own device. So similarly, an attacker can just send SNMP queries and just spam your device to cause high CPU.
Yeah.
Okay. I have maybe one question for you, Kris, now that the story is over on Datacenter. Sure. How do you see Datacenter and enterprise networks coming together? Because originally it was like, Datacenter, that's for very high speeds, that's for the data center. And then you had enterprise networks, which is just purely enterprise switches and so on. Now I see a lot of customers running data center devices, switches, Nexus device, as their enterprise switching. The whole campus is a data center, basically. So where's the limit? What's
It's sort of the same story as with white label CPUs versus ASICs that were specifically developed to do networking tasks. It made more sense in the past to have dedicated hardware that had specific use cases for a particular place in the network where it was positioned. At this point, we are up at 10, 100 terabit speeds of network. And we don't need specialized hardware as much as we do in the past. So you could actually, we sell that as an added value. The 7000 line for Nexus switches is completely modular. So you can configure it in any way that you want. Do you want a switch that's low latency performance? Okay, you can build it that way. Do you want a high capacity, high port number switch out of 7000? Sure, we have line cards for that. Do you want to mix and match? Most use cases will be able to do that. Not all of them, but yeah, in general, the point is that it has become so commodity. An Ethernet port in itself, both from how we sell it, as you would see generic components that speak Ethernet in there, is that it becomes difficult to make that differentiation. If it's more economical to build 10 gigabit ports than it is to build gigabit ports, why wouldn't you put 10 gigabit ports in all your devices? And then extend for the coming generations as well. So you would have a lot more performance in your enterprise network than you would typically need, not because you would specifically buy those products, because the products that are being sold to you as enterprise products have become commoditized on a higher standard. The people don't evolve as quickly as the technology does. Now, again, in data centers, we see an opposite evolution. We used to have a lot of very highly specific data center specific engineered products going out. Where if you look at companies like the FANG companies, the Googles and the Facebook, they're just like, okay, but we just need a switch to switch. We don't need a ton of features. We'll build our own one from off-the-shelf components, because they don't need complexity in their network. Complexity is the enemy there. So what you'll see is sort of where you would have a lot of complexity and management features and fine-tuning and bespoke networks for your data center applications. It's all just becoming more generic. More gets pushed into the application layer. Like that hyperconverged story where we started out, is a lot of that runs on commodity hardware, because all the difficult things about running a high-speed network or running a high-speed computing layer, they get pushed into the application layer. They get pushed into different parts of the stack where you wouldn't need to invest in expensive dedicated hardware, where you could do it very capably, I would say, in software or in firmware or somewhere in between your application and your layer one.
Basically, data center is a lot more customizable, right, to very specific needs, while enterprise products keep being very standard, indeed. Very classical use case.
And at the risk of repeating things that have already been said in previous episodes about the data center rampage, is we will become more and more challenged in whether features matter or whether speed matters or whether reliability will matter. That are shifting mindsets. Customers used to have a different profile of on-site engineers as well, where you would be having 5 to 10 years of experience with Cisco hardware just before you could get like a systems administrator position because of the complexity. That complexity is moving away. We're making simpler products, at least simpler to manage. The complexity still is there, but it's managed either more automatically or under the covers or in different places of your network.
Thank you, Kris. I do have another question, and it's a bit more of a more pedestrian question, a bit more simple. Yeah, sorry. I'm not a data center expert by no means, right? More in the service provider world. I hear a lot in data center about NAS and SAN. And to me, it looks like Mario and Wario in video games. You know, like the two enemies are the... What's the difference between them? Which one is the good one? Which one is the bad one, if there is such thing?
So from my FiberChannel experience, I will say SAN. SAN is more of a generic term nowadays. It's a storage area network. You see that they branded it to sound like LAN. A local area network makes sense. A storage area network, not so much. So people will just say storage networks. They don't implicitly mean FiberChannel with that anymore. And it's different technologies for different use cases. FiberChannel is very fast, very reliable, very low latency, low on features, has little expertise in the market. It requires expensive hardware that only a few vendors start selling. So you need a very particular use case to benefit from a SAN. However, if you have a distributed application, something cloud-based, Kubernetes, you can perfectly well do this with Ethernet and IP. You'll take the overhead because you'll put jumbo frames there. You just put more data in there. The networks become more reliable. So NAS has more features in terms of management, more granularity in terms of who do we give access to? NAS, in many cases, if you think about, for instance, NFS, Network File System, if you think about CIFS or Samba, the Windows Sharing File Protocol, if you think about WebDAV even, they have a lot more granularity in, for instance, file permissions. FC is a block level protocol. In essence, you don't have the concept of a user in there. You don't have the concept of write permissions. You have the concept of visible or not visible. there's a little bit more to it than that, but in its core, FC is a very low-level, non-granular, high-speed network for specific use cases, where NAS is a lot more flexible, a lot more featureful, cheaper to implement. What we did at a certain point in the FiberChannel team is we had interns from final year's master education. And we said, look, you're now going to build your own storage system because all the components are available in terms of hardware. You need some sort of a fast network card, you need some sort of a fast computer, and you need a few disk drives that are lying around that can hold some capacity for you. Your software components are there. The Linux file system can act as both a host and as a client. The application management thing, okay, write something in Python for your scripts. You want to do user management, okay, you can leverage whatever your file system offers you. So all those components are there. It's difficult to put it all together in a reliable way because, again, we're talking about the family photos and the bank accounts of people. So you need to be able to build it reliably, and that is the real challenge. But the complexity of the technology itself, it's like easy to learn, hard to master. And NAS is a little bit easier to learn and also hard to master. FiberChannel is harder to learn, but I would say easier to master because there's just less to know.
All right, thanks. That's nice. I think a nice summary of the two. At least now I think I understand the difference between the two. Thank you very much, Kris.
Chris, so thank you for the story. If people want to find you, if you want to be found, where can they find you? Are you on Twitter or LinkedIn?
I'm anti-social media. It doesn't make me happy, but I do have a LinkedIn page, which is in our line of work, sort of mandatory. So Kris Vandecruys at LinkedIn. If you type it in, there's two, but the other one is in construction. So go for the one that has something with computers.
Okay, and that's Kris with a K.
Mm-hmm.
Kris with a K. Yeah.
All right.
That's it. Thanks for having me, guys. Thanks for letting me share the story. And
thank you so much.
I'll go off and start editing.
Thank you, Kris.
Thanks for listening to this episode of the Cisco Tech Stories podcast. You can subscribe to us on Cisco Podcast Network and SoundCloud or in your favorite podcasting app. You can also find us on X at Cisco Tech Story without S. Thanks again for listening and speak to you next month.